Welcome. Today we look at calculus and economics. Each subject, and especially economics, has its own jargon. So a function which is of great interest is the marginal cost function. This is the marginal cost. Now marginal always means in economics that it's a derivative of another function. So this is then the total cost. So we have f prime of x is equal to f of x. F of x, capital F of x, is the antiderivative. And then we also look at the average cost, which is g of x is equal to f of x over x. So this is the average cost. Now these three quantities are related to each other in an interesting way, which is the strawberry theorem we are going to prove later. But let me just illustrate here what this means. So x is the number of goods, like the number of strawberries. And the function, this is here, this is f of x. This is the cost, giving us the cost of each good. And if we have some x here, we can look at, so this is f of x here, we can look at the area under the curve. That's an f of x. This is the total cost. This is the total cost until here. And the average cost is just, if you average all these costs from all these goods here, and then we get here, this is g of x here. G of x times x is equal to f of x. So that red area, that rectangle should have the same area than f of x. So these are the three quantities. We are going to formulate the strawberry theorem and prove it in the next section. The three quantities f, capital F, and g are related by the strawberry theorem. I will give you the reason for the name, but here is the theorem. First of all, we have points where fx is equal to g of x. These are called break-even points. So critical points of g are break-even points. That's the theorem. So g prime x is equal to 0 if and only if f of x is equal to g of x. So that's the strawberry theorem. So let's prove the theorem. First of all, what does it mean g prime equal to 0? So g prime is f of x over x prime. Now we can practice differentiation rule, like the quotient rule. You remember? Low d high, take high d low, cross the line and square the low. So that's what we have is low d high, take high d low, cross the line and square the low. So that's, now we take 1 over x out. So that's just f prime x minus f of x over x. And this is just 1 over x times the definition of f prime is just f, and the definition of f over x, that's the average cost, is g. So we see critical points are exactly the points where f is equal to g. So this is the proof. Quite easily done. That's what QAD means. So you see, it's kind of very, very poetic. It's very beautiful. There's just a derivative. If you look at economics books, how they prove it, first of all, the notation is completely different. It's a whole page of computation. And it's mainly because the notation is not optimal. So here in math, very beautiful. So here are some illustrations about Unit 31. we have introduced three types of costs: the total cost, the marginal cost, and the average cost, and then shown a theorem called the strawberry theorem. I just saw Emma, new movie 2020, and so the strawberry theorem tells that the average cost is maximal or minimal, has a critical point, even only if you have a break-even point. And I illustrate this in a separate movie. We have recorded this in 2013 using strawberries. So the proof is very simple, and I show this in the movie. And you see here the proof in the book of Heckner and Kretschmer, where I got that strawberry theorem from. It's also mentioned in the cartoon guide of Klein and Baumann. This theorem appears. Okay, in the second part of this economics lecture, we come back to another topic we have discussed, which is extremization. This has also to do with derivatives. So all we do here is really has to do with derivatives. And it's a classical problem in statistics. We have some data points like here, 1, 3, 2, 1, 3, 4, 2, 4, which relates some data. And what we want to do is we want to fit it, we want to find the best linear fit here. So usually the best linear fit is taken as a line, mx plus b, y is equal to mx plus b. That's what we do with the regression. So this is a regression line. That requires us to find two quantities, m and b, and that's more a multivariable calculus problem or a linear algebra problem. You learn that in 21b or 21a. What we are doing in here is single variable calculus, so we have only one, we look at only one parameter. So, but it's a reasonable problem. We are looking at the best line. What is the best line here, which goes through the origin? And so this is a line, y is equal to mx. And what is the best line when we want to minimize the sum of the squares of the errors? So that's what Gauss already introduced when he was also looking at astronomy problems. So what we want to minimize is the sum of the squares of the distances. So let me just write that down. So we have a function which now depends only on one parameter, f of m. So what we have is f of m, and what is this distance here? That's 3 minus m times 1. So 3 minus, let me just write it as m1 minus m times 1 minus 3 squared. So that's the same thing, right? That's this distance here, plus this distance, which is just m times 2 minus 1, plus m times 2 minus 1. And then we have the third point here, which is m times 3 minus 4. And finally, we have this distance, which is m times 4 minus 2. So we have the problem to extremize this. Now we know how to do that, right? We have learned that earlier in the course, and these application parts brings us back to this. What we want to do is we want to find whether the derivative is equal to 0. So we know f prime m, which is just Okay, let's look at another problem here. So the problem is to find the best line which passes here through the origin. Y is equal to mx, which minimizes the sum of the squares. Something which vexed me for a while. I would think, oh, this is so symmetric, like 1, 2, 2, 1. It should be y is equal to x, should be the best choice. But let's just see what we get here. So we have to take the sum of the squares. So the function which we want to minimize is the length of this square here. That's 1, 1. So this distance here is 2. This is mx. This is m times 1, right? So m times 1 is the height here, and this is 2. This is m times 1 minus 2 square, and then here this distance is m times 2, which is here, this point, m times 2 minus 1, plus m times 2 minus 1 squared. So we want to minimize this. Now we know how to do that. We have to compute the derivative and set it equal to 0. So this is 2 times m minus 2 plus 2 times m times 2 minus 1 times 2. So if you put that all together, this is 2 plus 8, this is 10m. And we get minus 4 minus 4 minus 8. So this is equal to 0, which means m is equal to 8 over 10, which is 4 over 5, which is 0.8. So the slope is not 1, the slope is smaller. In the second part, we look at the problem to find the optimal line y is equal to mx through some data points, which leads to an extremization problem. And so here is an illustration of that. We add just more and more points, and we always find the optimal line. And you see it kind of settles. In this case, it settles to y is equal to 3/4 of x, which is a little bit surprising. You would expect in such a situation that the y equal to x is the optimal line. The strawberry theorem tells us that break-even points are actually equilibrium points. So suppose you have all sizes of strawberries. That's what we have here, from very large to very small. Each size of strawberry exists twice, except for the smallest, of which you have only one. Let's just say that you line these strawberries up from very large to very small, then to very large again. So let me just do that. So we take a very large one, and then they become smaller and smaller. This is the smallest one, and then they become bigger and bigger and bigger again. Right. You take one strawberry after another and place them on a scale that tells you the average weight of all strawberries. So that's what we do. We start with a very large one here. We take it, put it on a scale, and we measure the weight. The weight is large, of course, at the very beginning. So the first strawberry that you place in the bucket is very large, while every subsequent one will be smaller until you reach the smallest one. So we do that until we reach the smallest one. Because of the linear weight of the heavier ones, average weight is larger than marginal weight. Let's just try to understand this. So we take this, and in each of the cases we compute the average weight, which is the average weight of these strawberries which we have on the scale, and the marginal weight. What is the marginal weight? If I take this strawberry, what is the marginal weight?
Just the way you add by
Exactly, that's exactly the weight of this strawberry. So what happens is this strawberry is lighter than the average weight here. Makes sense, right? Because these are heavier ones. So, and so on. So the average weight still decreases, also less steeply than marginal weight. So you see, because they are heavier here, so the average weight will decrease less than the marginal weight. Once you reach the smallest strawberry, and that's what we have just obtained here, every subsequent strawberry will be larger, which means that the rate of decrease of the average weight becomes smaller and smaller until eventually it stands still. So now, because the strawberry gets bigger and bigger again, we really reach a point where we have the average, where this is equal to the average.